Hi, everyone. It's great to see a full house today, so it makes us a bit excited. Today we have a great event, many nice sessions. So first of all, thank you for taking your time to attend our session. Today we will have about how and why GraalVM is becoming relevant for you, and the presentation will be done by the two Amisers, Lukas Jelema and myself. So without having any delays, because we have so much interesting stuff to show, we will start immediately with a short demo to catch your attention. So if you allow me, we want to show you a few things. So what I have here is a small Java application. Just to show, it's almost a hello world, but it does a bit more. So we have in a modern style developed a Java application that uses a stream API. It reads a file and then does a couple of character manipulations. At the end, it will sort out our file to get the most frequent words appearing into the file. So I want to show you we are going to run it. I have already, to save some time, I have already pre-compiled this application. We are going to run it with the time option and add a verbose option to it to catch the startup time and the memory usage, because that should be the interesting I'm quite nervous, so why is it not running? Okay. Demos are always going a bit, so thank you. It's a Java application, right? It's still not working. Now we have to add a class.
Go to the presentation. The point we were trying to make, and we will make it later on as well, is how running a Java application as is, even on GraalVM, gets you certain performance. But when you start using the ahead of time compilation options and turn your Java application into a binary natively executable image, it can run much faster, because you don't get the overhead of the full Java runtime, you don't get the overhead of the initialization and the startup time of your Java runtime. You also don't get the runtime optimizations of your Java runtime, but frequently those aren't all that important, but your startup time and your memory footprint are.
So I got it run. I didn't I didn't give it a file to process. So by running this small application, sorry for me being a bit nervous, it's a full room here. So we are processing the file.
It's your fault, actually.
So we are processing, we are doing something we have a startup time of 50 milliseconds, and we have a resident memory of 140 megabytes, which is by itself a decent result. For a Java application, it's not the best, but I have been running bigger microservices with the worst startup time. So this is the traditional way of compiling your Java application. What we want to show is the GraalVM way of compiling the application. In this case, as you can see, we are running something that is called a native executable without a Java option. So it should be an instant machine code that we are trying to get here. And if we run this, wow. So we get the same result. The file is processed, but the startup time is 2 milliseconds, which is impressive, at least for us. And if you look at the memory residence size, it's 30 megabytes. So we have increased the startup time by more than 10 times and reduced the memory almost 5 times, comparing to something that was already on a decent level.
It's exactly the same application that's running, but after compiling it into Java class, we took the additional step of doing the ahead of time compilation rather than the just-in-time compilation that we usually use. That's what's getting you the much faster startup and a much smaller memory overhead. So there's so much we could say about GraalVM, and we won't be able to cover everything that there is to say about GraalVM, but some of the keywords on this slide should give you some trigger points. If in the future you run into any of these areas, think of GraalVM. And you may have heard about GraalVM for many years because the research project was started back in 2010, but now it's production ready. That's what's one of the reasons why we are here today, why you are probably here today as well. And we're trying to give you a brief overview and then dive into two specific areas. So where does the name come from? Of course, we know the word in Dutch. It doesn't really exist in any other language. It seems to be a reference to, well, the Holy Grail of programming. And there are several types of Holy Grail and several reasons why you might want to have Holy Grail. And you see maybe the spaghetti code mentioned in this cartoon. And actually, that's not so far from the truth in this case, because we were having a problem in the Java community with the C2 compiler, the compiler that kicks in at runtime to provide optimizations to our Java code as it's running. And that C2 compiler, written in C++, had become a big bowl of spaghetti. It was unmaintainable. It didn't really work very well for modern language concepts, not in Java, certainly not in Scala or Kotlin. So we needed a plan, and I say we, I wasn't necessarily part of it, but we as a community needed a plan because we were getting stuck with this C2 compiler. And that's where the GraalVM project originally started, to get us a new just-in-time compiler that allowed us to run Java applications and other JVM applications much faster and have a compiler that was actually maintainable. And then GraalVM turned out to be much more than that. It turned out to be also the polyglot VM that not only runs Java, but other languages as well. And that supports ahead-of-time compilation, as Adnan was just demonstrating, and we'll discuss in more detail in a moment. And not just run applications in different languages, but run them intermingledly, have them interoperate at runtime, as we will see in the last section. And you can even add your own languages. And GraalVM comes with a bunch of tools that you can use across all the languages. So it's really almost a whole ecosystem by itself. And I've tried to visualize it in this picture, but the different areas of this picture will become more clear as we progress through the presentation. You can see the different languages that are absorbed by the Graal platform and can be run by the Graal platform. The Truffle framework is the part that takes care of absorbing languages that are not JVM languages and turning them into an abstract syntax tree that's expressed in Java bytecode and then can be run on the JVM. We see the substrate VM, which is a very small component that will be part of every binary executable created with ahead-of-time compilation. That's all we're going to tell you for now. So where did it come from? As I said, it originally started back in 2010. It was spun off in 2012 as a separate project. And then it sort of gained momentum through the years, and especially in the last year and a half. We've seen the first public release, we've seen the first general production release, and we see many other frameworks now taking up Graal as their preferred JVM, or at least providing support for Graal. One of the biggest references is Twitter, where they started in 2017, so that's more than 2 years ago, with running all their Scala applications on GraalVM. And this morning, I was in a session where a case was presented for the Dutch National Police, where they are also using GraalVM for the interoperability between Scala and R. More about interoperability in a moment. GraalVM comes out of Oracle Labs, which used to be Sun Microsystem Labs, which produced many beautiful things. And at this point, Oracle is providing it both as an open source option, a community edition. That's fine for most use cases. They're also providing, of course, an enterprise edition where you get more options to even further fine-tune performance and also get support. But of course, this is a paid option. Graal's many things, but today we will have to focus. And even in the 15 minutes we have, it's hard to tell you everything we would like to tell about ahead-of-time compilation, about polyglot and the interoperability. We'll start with diving into the ahead-of-time compilation. Adnan, back to you.
Thanks, Lucas, for the nice intro. So I will start now with, Lucas mentioned the multiple things that Graal VM does. It's kind of multiple projects that are coming together. In this part, we will focus on how Graal VM handles the JVM-based languages and what are the new things from Graal VM. So let's see how it compiles. So Graal VM provides two compilation modes. The first compilation mode that I want to touch here is the just-in-time compilation mode. This is the default compilation mode for the JVM application. So if you run your JVM application currently, it will be compiled with JIT compiler. So the JVM is a runtime engine. So to start with, so it will load your classes, it will interpret your code, it will then run JIT compiler to compile it, optimize it, and produce a machine image while your application is running. So this is a specific thing for JVM-based applications, and it means basically that your application, as long as it's running, it will get more optimized and faster over time. This is a very specific thing for a JVM-based application. That's also the reason why Java can run fast as it runs. So in some cases, it can even compete with the C++ languages. But your code gets optimized while it's running. How many of you are familiar with this option? Okay, so many people are familiar with this. We are not going to go into that. But basically, Hotspot JVM Hotspot provides two compilers. As we mentioned, there is a lightweight C1 compiler. As we said, it first interprets your image, but the difference between the interpreted speed and the final machine code is huge. So you want to have an intermediate solution. And that's why this lightweight C1 compiler kicks in to produce your first machine code of your application. And then it will monitor how it also you use your application. So it will collect the profiling data of how your application is run. And when some of the classes are becoming really hot, it means that they are invoked around 10,000 times. Then the heavyweight compiler, C2 compiler, will kick in. And based on the profiling data, on the data that is collected from the startup, it will produce a second machine code, which is a highly optimized. And that's why we get it so fast. As Lucas already mentioned, those two compilers are quite old. They are existing for more than 20 years. They have been developed in C++, which is not necessarily bad, but it's very hard to maintain this base of code. And there have not been significant improvements on those compilers for the last few years. However, how we use Java application today and how it was used 20 years ago, it's quite different. So the C2 compiler is very good for the traditional workloads, but it has not been really updated to cope with the modern workloads that we are facing today. And that's exactly where the Graal VM is kicking in. And in this context, Graal VM is tending to replace the C2 compiler to provide this highly optimized options for the modern style of Java programming. And when I say modern style of Java programming, think about things like Scala, like Kotlin. Also use of the streaming APIs. Even the lambdas use modern syntax of the Java. It has been more optimized or more focused through the Graal VM. And this is also the domain where we have currently only production use of Graal VM, which is by Twitter. Twitter is using the Graal VM for compiling in the JVM mode, compiling their Scala microservices. So I said Scala concept, it compiles to the Java code, but the structure of the code that hits the compiler it's a bit different from if you would develop the same application in Java setup. So this is where the GraalVM in the traditional JIT compilation, the traditional JVM world, aids a lot of benefits for the application developed in the modern style. But we will focus further on a second part of the second mode of the compilation provided by the Graal, and that is ahead of time compilation. So this type of compilation is unique to the GraalVM. You will not get it by the other JVM options. Ahead of time compilation is specific is that GraalVM is capable to take your application, load all the dependency, take the parts of the GVM, add something that is called substrate VM, and create your machine code while you're compiling before running it. So it will produce a native executable that you can run by itself without using the GVM.
And of course, it's platform specific. It's
Yeah.
a native executable for the native platform that you created for.
It is platform specific. But let's look a bit deeper what's happening. So as I said, GraalVM does something that's called closed world assumption or closed world analysis. So it will assume that your application has all the classes necessary, all the libraries, JDK and substrate VM will take it, and then it will run an analysis on everything. So it will start with to check which all classes are reachable from your main application. It will then check the relationship of those classes, initialize them, and create an image, snapshot. And it will go through the iterations to check until it goes through all your application and check all the classes. We are doing this because we want to package only what is used by your application. So the compiler will check only what is used by your application and how it's used, try to initialize that and package that so that we get a very minimum in your package, and everything will be pushed out to the native executable. So in the section of machine code, there will be your AOT compiled code, and in the image heap, there will be those preloaded methods and the classes. So it helps you also to initialize your application on your startup. This is also the reason why we're now able to run a Java application in 2 milliseconds. Most of your application is already all of your application is already compiled and initialized before you run it, which is different from Justintime, where we are doing the optimization while we are running it. So this output, this native executable, still has some runtime in it. So that runtime is provided by the substrate VM, but it's very limited comparing it to the JVM runtime. So this runtime will provide us some features of the garbage collection. However, they are much less advanced than the garbage collectors that we have in the JVM. It will not have any interpreter code, or it will not have any JIT compilation. It will not collect the profiles of how your application is running, but it has some runtime in it. Because of this closed world assumption, that we are assuming that everything that your application needs, it will be available when we are building or compiling the code. This is quite different from how the JVM was expecting that your application will be running. So there are some limitations with this approach. The biggest limitation, or the main limitation, which is more logical, is the dynamic load of the classes. So as we are creating that optimized machine image before we run the application, there is no room really to load additional classes during the runtime. This feature was used by enterprise Java applications. So there are features where you can deploy your application, it runs, and then over time inject some additional classes to it. This will not work with ahead of time because of whole concept. We are compiling it before we run it. Next thing of this list, reflection, which is very important, and this is something that we really need to do. And reflection is in some cases, in the basic cases, is automatically recognized by GraalVM and handled. In more complex cases, it needs additional configuration. And when I say additional configuration, it's more about flagging and making the compiler aware about your reflection cases, because it needs to collect all that's needed for reflection while building the image. It's supported, but with additional configuration.
And it basically means that you provide a list of all the classes that you will load dynamically at runtime.
Exactly.
Yeah.
So you flag them.
That's not that hard.
It's not that hard. I'm not going to go through the whole list. There are some things that may be a bit shocking for some security manager, but security manager, as we are not loading additional code in our application, there's no really need to sandbox those classes or do any security. So it's not really needed. There are some other VM native interfaces like GMX, and those interfaces expect to rely on your Java bytecode. And we don't have the Java bytecode in the native image anymore, so they are also not supported. If we want to compare those two models of compiling the code, and we will compare them based on some of the benchmarks. So we can see that ahead of time compilation is more focused on the startup time, quick startup time, low memory footprint, small packages, things that are becoming very relevant where we start moving to the cloud. When we have start moving to the cloud, when we have start adopting the microservices architecture concepts, those things have become very relevant, and it was a bit a shock for the Java community that our Java applications, our microservices, are not behaving that well comparing to some other languages in the beginning. So I remember that 3 years ago when I deployed my first microservice using the Spring Boot, the memory footprint was around 400 megabytes even, which was shocking comparing to the JavaScript, or even it was Go relevant at that time, but we didn't want to really start learning new languages. We want to do what we are good at and continue. So benefits that IoT is providing in the Java world are very relevant for the microservices and the cloud native development. However, if you look at some things which is peak performance, peak throughput, or JIT is still much better for that, because this whole nature of constantly collecting the profiling data while your application is running and optimizing it, it is able to provide very high peak throughputs. And reduced max latency is also as a result because IoT has very limited garbage collection options, while hotspot and GVMs have a low latency garbage collection, so they are able to provide better results in this. I also want to mention here that even if we put aside a bit of this benchmarking, it's also very important the nature of how you run your applications. Because if your runtime is measured in days, weeks, months, then probably the JIT compilation mode is more fitted for those use cases. Because in that case, when your application is running for a longer time, you will give enough time for the JIT compiler to optimize, to provide that high optimized machine code for you and to run your application very fast. But however, we are entering now, as I mentioned a couple of times already, microservices, cloud native, even a function world where the runtime is measured in hours, minutes, seconds, milliseconds. Then there is no room for this continuous improvement to happen. And IoT is providing us a nice mechanism how to compete with other programming languages in this domain. So as I mentioned already a couple of times, we are running out of time. A couple of times there are at least 3 frameworks available on the market that have adopted the GraalVM native image as a baseline for their development. Helios provided by Oracle, Quarkus by Red Hat, and interesting is maybe to see that all of them are advertising in the microservice domain, lightweight microservices. So as I'm running a bit out of time and I want to show you some of those things happening, so I want to jump into the nice world of Quarkus. And here we have a small Quarkus application. We have shared the links. If you go to our GitHub that has been shared as part of the presentation, all the code is available. So we have tried to make it easy for people that want to have some hands-on and learn about those topics. So there is a Maven plugin that you can run that will create your small application, a Quarkus application. It's basically a hello world produced by Quarkus. There is something called Maven dev mode provided. Yeah, today is not my day. Compiled Quarkus stuff. Development mode provided by Quarkus. It's a live compilation mode. So it's something that we have seen in JavaScript world for many times. So when you change something on your code, so if I go, hello, nothing special. Yeah, this works. But if I go and just click Control S, it will automatically recompile my application and sit. It is new for Java world. It's nothing special because this already exists in the JavaScript world from the beginning of the JavaScript itself. But what I want to show here is something that you get with the Quarkus, and they are advertising as the cloud native framework. So as the part cloud native, you get two predefined Docker files for building your Docker containers. And this is where it gets very interesting. So if you just follow this, so let me just. My application, and I will package it using this script. So this is the traditional JVM packaging. And I can run it even.
It failed.
It failed. What did it fail?
Didn't find sources.
Live demos. I have tests, and test is always good. So now it works. This also now works. So where were we?
So you just build the container, now you're going to run the container.
Yes, we have packaged the traditional JVM style, our Java application, and we want to build a container out of it and to run our container. Why do I want to do this? Because there is another Docker file, and in this is also important to see that it will use Alpine Docker image, which runs OpenJDK 8. So traditional way, we need a JVM to be part of our Docker container to run the application. So this is clear. If we switch to the native image, then we will have to repackage our application, providing additional options. So let me just run. This will take some time. As Lucas already mentioned, the native image will be machine dependent. So if I but it's nothing that it. Trying it again, it will not make it.
Could be a network issue.
My port is used. Or what to do.
Ga maar door, ga maar door.
So what I wanted to show here, but I have to show this, sorry. No, test is not the problem. Thank you. It's good to do it with the Java community. No, I'm a bit... So we have provided this native image Docker build. It will give instruction to Quercus to build my code to run in a Docker. So if I build it this way, it might be that I'm not able to run this machine image on my laptop. Because as we said, machine images are related to your machine. So what? Yeah. So it takes some time. So he's really compiling my code. So he's doing that closed world assumption, where he's taking all the libraries, all the dependency, analyzing them, throwing away what is not used, packaging only what is needed to produce that lightweight image. So that process is currently running. It should be done very soon. So please give me some, because the result is going to be spectacular. So we have built it right. No, we have to build a Docker. This takes a second. Successful, luckily.
Is the port available?
I have to put it on a different port. Let's put it on the port 82. And if we go to the Docker stats just to see our containers running, yes. So we have one container with 4 megabytes, other container with 100 megabytes. So the native image in a Docker runs on the 4 megabyte. And I'm telling you, I have run microservices at 400 megabytes. This is 100th time optimization improvement. And what is very important, that this improvement is directly aiming on your cost of your application on the cloud. So you are paying how much your application is using the resources in the cloud, where the memory is one of the most expensive resources. To have the ability to get down your code by 50 or 100 times, it's really impressive. I had some other things to show, but yeah, we are a bit running out of time. So, do I have still?
No.
Nee.
Ja.
Sorry. So what I wanted to show further is extensions. So the Quarkus, the community is also working on building other extensions. So you want to use the frameworks like you have been used in the Java world, also in the new frameworks. So there is a huge community of frameworks available, connectors. And it also has the support for the cloud, AWS or the Azure functions. We have prepared some examples to show you that, but yeah, we are a bit limited of time, and this other part of the presentation is going to be even more interesting.
Not more interesting, it's also interesting. We could really have done with 2 slots. So the polyglot platform, language interoperability. Why do we even have so much languages, so many languages? It's history, well, there are people who think they know, this is the flag for Esperanto, you probably didn't know that. There are people who think they know why we have all these languages. We won't go into discussion, we certainly don't have time for that. But we do have them. There are cultural, historical reasons. We don't want to learn necessarily a new language if we already know one. And some languages are better suited for certain purposes, like poetry or laws, than other languages. And of course, in IT, we have the same situation. We have many languages. There are reasons for their existence. Maybe not all of them are still valid, but hey, they are here, and we better deal with them. So in the world of real languages, we talk about polyglots. And polyglots are people who can speak and understand many different languages. And in our world of IT, in our world of Java development, there's also this polyglot thing, and that's GraalVM, obviously. And why is it polyglot. In which way is it polyglot? Well, it can run languages, all kinds of computer language applications written in different computer languages on the same JVM infrastructure that we use for Java application with all the benefits of that very mature infrastructure. It can run obviously Java, it can run all the JVM languages, no surprise there, but it can also run many languages that are not related in any way to Java or the JVM, and it does so through Truffle, I mentioned that before, and we can even take statically compiled languages such as C, C++, Swift, and Rust, use the LLVM, which is kind of a polyglot thing in itself, and take the output from there and run that too on GraalVM. So that's what GraalVM polyglot means. It can run applications written in all these languages. It can be the runtime for all applications, regardless of the language they're written in, even your own language. But then there's also polyglot interoperability. It basically means that we get frictionless interaction between different language contexts. That works in the real world, in our world, where we have human languages, but hopefully it also works in the world of computer languages. And of course it does, otherwise I wouldn't be standing here. Currently on the JVM, if you want to establish interoperability, you have to do things like this, but they're all no good. Either because they're no fun, or they don't work very well, or they introduce a lot of overhead. We don't really like any of these. And with GraalVM, we get interoperability in the way we would like to have it. And it's not all that hard to understand what's happening. When you think about all these different languages, we know that basically they all are used to describe similar concepts. We all have the word for table, but it's different in different languages. We have the same concept. And once we get to communicate about the concepts, we can have a meeting of the minds, even if the minds speak different languages. And the same thing really applies to computer languages, where all these languages express similar concepts. And these similar concepts from programming, like variables and loops and conditions and basic arithmetic, if we take these concepts from all of our languages, we can turn it into this abstract syntax tree, which in the end, of course, is turned into bit manipulation for any language. But even this abstract syntax tree can be defined in the same way across languages. And if we then find a way to take this abstract syntax tree, turn it into something we can run, we're in business. We are in polyglot interoperability business. And we don't have to do that. That's what the GraalVM team does for us. So GraalVM provides a polyglot engine where you can run bits of code, or not necessarily bits, pieces, snippets, fragments, libraries of code in different languages and interoperate. Have one language start the application and start invoking fragments written in different languages. So we used to have Rhino and Nashorn, which provide, I never understood why they were called after neushoorns. I don't really get the point. But anyway, they go out and we now have a new beast for doing the Java to JavaScript interaction in both directions. And not just Java to JavaScript, by the way. So what we get in Java is the ability to evaluate JavaScript snippets, to load and call JavaScript sources, exchange data, allow JavaScript callbacks, and even run multiple JavaScript threads from a single application, which of course JavaScript by itself cannot do. Well, it's now starting to do something like that with the worker threads, but basically that's not what it does. And what applies to JavaScript on this slide applies to all the other languages that GraalVM and Truffle support as well. So here's an example, but maybe I should show it live. And for that, unfortunately, I do need glasses. That's a new feature. Such a mature language. So here we are in Eclipse, and of course it's hello world. This line is where we declare our willingness to engage in polyglot interoperability. Let's create a context. And here is where we do our first polyglot thing. We evaluate a JavaScript snippet, which is shown here. So basically, here's a JavaScript code, please execute. On one hand, it's not spectacular, especially given this particular JavaScript snippet. On the other hand, it's extremely spectacular. We're running a Java application, all of a sudden we're doing JavaScript things in the middle of our application. Here it gets a little bit more interesting. The JavaScript snippet is defining a function object. And it's returning the function object back to the original context, which in this case happens to be Java. So now in our Java code, we have this object, which is a function object from JavaScript, which is defined by JavaScript code, doing JavaScript things, but we have access to it from Java. And the next line over here is where we actually are executing that function, which is basically a JavaScript function. And finally, an example where the JavaScript snippet is throwing an exception, and we are catching and handling the exception in Java. So if I run this code, the output isn't spectacular, as I said, but what went on is quite spectacular. Java was compiled to Java bytecode. Java bytecode is run. In that Java bytecode, there's this call to JavaScript. The JavaScript is interpreted at runtime, turned into Java bytecode, and executed as well. It is quite spectacular, and Hello World really doesn't do it justice. Here's an example of a callback. So what's happening here? Create the polyglot language context for JavaScript, get the bindings map for that particular context, which is kind of an exchange area where the world of one language can store objects and data that are then available to other language contexts. All other language contexts, by the way. So we could define something in Java, make it available to JavaScript, have JavaScript manipulate it, and then call out to Python, have Python have access to that same object. So here we put in a Java object that's instantiated here. The new friendly neighbor, well, the new friendly neighbor doesn't do much. It just returns a string. It's nice, but still, it's just a string. Let's add a few exclamation marks. So this Java object is put in bindings, and here inside of JavaScript, we access that Java object. So it's put in bindings under the key friend, and it's available in the global context in JavaScript under the key friend. And on this Java object, there's the method good morning. So in JavaScript, we can execute good morning. And if I run this code, take note of the exclamation marks. It's a live demo. Could easily have failed, of course. We can do the same thing with Java to Python, Java to R, Java to Ruby, even Java to C, or Rust, or Swift. Here's this bindings object. As I said, it lives in the polyglot area between Java and all languages that you invoke from Java. And it's we use it to store functions and data objects. They can be executed from both ends. We use an example of a JavaScript variable called pi. It's stored in bindings, and Java is then reading that variable. Of course, this particular example isn't necessarily very useful, but it gives you an understanding of what the bindings object is and how it really is shared between the two worlds, the two language contexts. Here in Java, we instantiated a map, put the map in bindings, and access that map from JavaScript, where in the JavaScript world it's just a JavaScript object. It can be accessed, manipulated, and returned or shared really with the Java context. And this is the callback you already saw in the demo. So this is a typical challenge. Not just a Java challenge, by the way, but in this case it is a Java challenge. I am developing a Java application, and in the Java application I need to do all kinds of validations. Post-code validations for 30 different countries. And I could start to write that code all by myself, but I would like to leverage something that's already out there. And in this particular case for validations, there's this NPM module, which can do all kinds of validations out of the box, but it's written in JavaScript. And of course, that used to be something we could see but not quite get at as a Java developer. Now we can, actually, quite easily. What I'm trying to do is create something like the following pseudocode, where there's this postal code validator that I can simply invoke to perform a validation on a postcode. That's what I would like to have, but I currently don't have this postal code validator. It's not an existing Java class, and this npm thing is something that I haven't gotten to yet. So here's the npm module, and here's part of the GraalVM site where you can evaluate if a particular npm module or Ruby gem or Python library is already supported by GraalVM in a sense that it can be interpreted and run on the JVM. And in this case, fortunately, the validator module is supported by GraalVM. So the next steps are I use GraalVM as my runtime, not just any regular JVM. I install a bunch of npm tools, and then I use Webpack or another JavaScript bundling tool to turn the JavaScript module, which is composed of dozens of different JavaScript files, into a single file. That's an important step, because Java and even Graal running Java currently does not understand the npm module structure. There are solutions, this is one of the solutions. And then I can embrace in my Java application this particular piece of JavaScript code without actually touching it. I'm just loading it and making use of it. So back to the demo environment. Here, I'm loading this bundled JavaScript module. It's the npm module turned into a single file by Webpack. That's all it is. I haven't touched it. I haven't even looked in it. I don't really care about it. Here in my polyglot language context, I evaluate the source that's loaded from this particular file. So this is where it's turned from JavaScript into Java bytecode. That's a very shortcut way of putting it, but it gives you the right impression. At that point, I get a list of, I'm printing out a list of all the functions that have been defined in that JavaScript and that are now available to me in the bindings object. And then I have my postal code executor. So I get the particular validator that I'm interested in. It's called isPostalCode. I get it from the bindings object. I store it in this variable, and it's actually a function object, so it can be executed, and it's executed in the next line, and I can simply pass the parameters it requires, and I get, of course, the validation result. So when I run this code, the first line tells me all the functions that are now available in Java provided to me from JavaScript, and I can invoke all of them to perform all kinds of validations. Sure about that? That's a bit of a problem. Time related. And I get the validation result. Okay, no more demos for you.